This is the third lecture in the first unit. This will be an overview of some basic chemistry. While this is not a chemistry course, we will cover some chemistry basics which will be useful in understanding certain physiological processes. The smallest unit of individual chemical makeup is the element. These are represented by the different chemical symbols on the periodic table of elements. Only a limited number of these are used in the human body. The atom is the smallest unit of an individual chemical makeup or an element. If you remember the simple model of an atom you learned years ago, this same model will work for you for what you need in this course. In the center you have the nucleus. The nucleus contains the protons which have a positive charge and the neutrons which have a neutral charge. Around the outside you will have the electrons, which have a negative charge. In a neutral atom you will have the same number of protons, electrons, and neutrons in the atom. The electrons are arranged in shells or layers around the nucleus. The first shell holds 2 electrons, the second holds 8. The elements that fill these first 2 shells will be the ones seen most frequently in anatomy and physiology, or A&P. According to the formal definition of a molecule, it is made up of 2 or more atoms of the same element. This would include things like oxygen gas, which is 2 oxygens. Despite the definition, molecule is often used when talking about things like water, even though it is composed of 2 hydrogens and 1 oxygen, and technically is a compound. Compounds will contain more than one element. The atomic number, which is a whole number on the periodic table in the box with the chemical symbol, tells you the number of protons, neutrons, and electrons in a neutral atom. Also, on the periodic table you will find the atomic mass, which gives you the mass of a single atom in atomic mass units, or AMUs. Here are a few of the most common elements found in anatomy and physiology. Knowing the chemical symbols of these is helpful, and most of them are pretty easy to remember. These include oxygen, carbon, hydrogen, nitrogen, calcium, magnesium, phosphorus, potassium, sulfur, sodium, chlorine, and iron. Free radicals are something you will encounter in anatomy and physiology. These have an unpaired electron, which is not a stable state for a compound. These are very reactive and destructive and have implications causing disease. They are also associated with the aging process and are thought to play a role in certain cancers. The body neutralizes these with antioxidants, which work by sacrificing an electron to the free radical to spare the tissues. Not all antioxidants work in all locations or on all free radicals, so the research suggests we are better off to take in a variety of antioxidants rather than large amounts of just a few. The major antioxidants are vitamins A, vitamin C, vitamin E, and selenium, although there are several others which are valuable in trace amounts. Now we will take a look at how atoms are held together. One of these bonds is the ionic bond. This involves the attraction between positive and negative charges. In the example provided, sodium has only 1 electron in its outer shell. The outer shell is most stable with 8 electrons. Rather than acquiring 7 more electrons, it is easier to release the single electron. This leaves sodium with 1 more proton than electron and a net positive charge. The chlorine has 7 electrons in its outer or valence shell and is only 1 away from being stable with 8 electrons. It will accept the electron given up by the sodium and now have more electrons than protons and become negatively charged. Now the sodium and chloride are held together with an ionic bond due to their positive and negative charges. In covalent bonds, the atoms will share electrons. In the picture shown, carbon, which has 6 electrons, 2 in its first shell and 4 in the outer shell, is able to share with 4 hydrogen. Each hydrogen has only 1 electron and would prefer to have 2 in its valence shell. In order to satisfy this, it is willing to share its electrons with carbon in order to have access to an electron. Carbon is able to do this with a total of 4 hydrogens in order to have access to a total of 8 electrons for its outer shell. In some cases, a carbon will even share 2 or 3 times with a neighboring carbon to form double or triple bonds just to fill that outer shell. In hydrogen bonding, one of the atoms is more electronegative than the others it shares an electron with, or has a greater pull on the shared electrons. The atoms do not share electrons equally, just like 2 different age or size children often do not share toys equally. This causes the electrons to spend a greater amount of time closer to the more electronegative atom, or a larger child giving up its partial negative charge. The atom with the lesser attraction to the electron ends up with a partial positive charge. So in the example shown here with water, you're going to end up with the oxygen having a partial negative charge from pulling the additional electrons into its area, and the hydrogens with a partial positive charge from not being able to hold on to those electrons. In a hydrogen bond, there is an attraction between the partial positive and partial negative charges, similar to the ionic bond, but it is created by unequal sharing of electrons in a covalent bond rather than transferring electrons. This example shows the attraction of the partial charges of water. This allows water to hold or stick together. These bonds also help to stabilize proteins when they are folded up together. We're now going to watch a short video clip on bonding.
Ionic bonding occurs between 2 atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with 1 valence electron needs 1 additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still 1 short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
The bonds that hold molecules and compounds also hold energy, known as chemical energy. When a structure is built, it requires energy to be put in to make the bonds. When a structure is broken down, the bonds are broken and energy is released. Reactions that build things are known as synthesis reactions, while decomposition reactions break things down and release energy. This can be seen when you look at a pile of leaves decomposing or rotting leaves on a fall morning and see the steam coming up from the pile. As the chemical bonds in the leaves are broken down, energy is released in the form of heat and seen as steam coming out of the pile. In the world of chemistry, the word organic is used differently than in the food industry. When referring to organic chemistry, we are talking about the chemistry of carbon, or carbon and hydrogen, where carbon is the central atom. In inorganic chemistry, sometimes referred to as general chemistry, all of the elements are studied, including carbon, but carbon is not central. Both of these branches of chemistry have enough information in them to easily fill at least a year of study each. The hydrogen bond gives water some unique properties. It is also a large portion of what makes up the human body. Water can be a medium for reactions to occur in. As a medium, it allows things to interact with each other, much like when you make cookies. Your dry ingredients don't actually combine with each other until you add the wet ingredients that act as a medium. Water also participates in the reactions, just like when the wet ingredients participate when you bake the cookies. Water absorbs and releases heat slowly, as well as requiring large amounts of energy as heat to form a gas. This explains why the ocean off the Washington coast is nearly the same temperature all year long. Even in a week of non-stop hot weather during the summer, it is still not enough to make the ocean warm enough to swim in. It would take several months to begin to heat up the ocean. This is beneficial for us as humans because otherwise we would rapidly evaporate in warm environments. Water may also act as a lubricant in the body and can be a significant component of fluids providing lubrication. Solutions involve combining solids into liquids. The solvent is the liquid which allows the solid substance to break apart or dissociate. The solute is the solid substance that dissociates. The combination of the dissociated solid and the liquid is referred to as the solution. The pH is the percent hydrogen or potential hydrogen. When water dissociates, it cannot split equally since there is only one oxygen. Instead, the oxygen will go with one of the hydrogens, and they take the shared electron from the other hydrogen with them, creating the hydroxide or hydroxyl ion with a negative charge. The other hydrogen is left without its electron and is a positive hydrogen ion. More free positive hydrogen ions are more acidic, while more free hydroxyls are more basic. The pH scale runs from 0 to 14, with 7 being neutral. The scale is logarithmic, with each change in a whole number representing a tenfold change. The acid end runs from 0 to 7, and the basic end from 7 to 14. A pH of 5 is 10 times more acidic than a pH of 6, while a pH of 12 is 10 times more basic than a pH of 11. The pH is important in regulating many body functions, therefore we do not want it to fluctuate too easily. The body uses chemicals known as buffers that are able to help absorb pH changes so they do not occur too drastically. Each buffer has a specific pH zone that it can buffer and has limits as to how much it will buffer. There is a link to an additional video here that is about 13 minutes long that gives more information on the pH if you would like more clarification on this topic. Additional activities for this section would be to follow the suggested links, read through information with the intent of letting it reinforce what is covered in this lecture. Remember, this is to familiarize you with the chemical terms so you can understand them in the context of anatomy and physiology. At the bottom of this page, there is a link also available to complete a tutorial to help reinforce this information.